Once again, we're in serial analysis. We need to choose the base problem that corresponds to the one that we're solving here, which is levitation RZ. We need to add values. In this case, I'm interested in mechanical force that's acting on the magnet. Now we will record steps. I'm going to displace the magnet to the left in increments of 1 centimeter. Let's add a step. And I'm going to repeat the last step a couple times. Okay, one more. Now let's get the results. So it's now solving the problem and translating the magnet. So first we started off with 0.22 newtons. Now the force has decreased to 0.11 newtons as we've moved it 1 centimeter. So if we want to know the distance that the magnet is going to levitate above the superconducting disk, that will correspond to the distance where this magnetic force is equal to the gravitational force, or mg, of the magnet. And we're down to 0.06 newtons. Now because this boundary is closer here, these force values are going to be not quite as good as if we had pushed the boundary out farther. It is still decreasing, 0.03 newtons. We're now 4 centimeters above the superconducting disk. In our base problem, we were 1 centimeter above. And finally, we have 0.17 newtons. And we can plot the results. We can plot the force of the magnet. And then find the optimum distance that the magnet will levitate, knowing what the gravitational force is. Next, I would like to look at the stress distribution for the same problem inside of the superconducting disk. And that is going to require coupling the magnetostatic stress to the stress analysis problem. So let's look at the solution for the magnetostatic problem. It's already been solved, so we did previously. Okay, now I have a stress analysis. I want to look at the geometry here. Now the geometry file has to be common for both the stress analysis and the magnetostatic problem. So they both have the same model file. Now if we look at the block labels, I have an air region, I have the magnet, and the superconductor. Now in the stress analysis, I am not interested in the stress distribution in the magnet or in the air region. There's no stress in the air region. So in the superconductor, I need to specify the Young's modulus, the Poisson ratio, and the shear modulus. For YBCO, we have a Young's modulus that is about 95 gigapascal. Now, I've assigned an isotropic value. However, I can assign anisotropic values. For example, in YBCO, we have a slightly different Young's modulus in the z direction, or the so-called c-axis, the Poisson ratio 0.3, and finally we have a shear modulus that we can also make anisotropic. Now I need to couple the magnetostatic forces into the stress analysis problem. And I've actually done that here, but I will show you where you would do that if you have, I'm looking at the stress analysis here, and I'm going to edit the properties. And I'm going to look at my links here. So the data type is magnetic forces from this particular problem where we saw the magnetostatic previously. Okay, I can update that. So I have a link now between the problems, and I can solve the stress analysis. It had already been solved, but just illustrate that again. Okay. So here's the magnetic field that we have surrounding the disk. And this is the stress distribution. This is the von Mises stress in newtons per square meter. Also, we have a deformed boundary of the superconductor. So we have a magnet in this region that's exerting a force to the right on the superconducting disk, and I've essentially clamped the superconductor here. So we have a boundary where there's zero displacement in the radial or the z direction here. So we always have to have a boundary where there's no radial, and I need a boundary where there's no z displacement as well. Now this is not the true displacement. We have essentially multiplied the true displacement by a factor of 10 million. Okay. So the true displacement, you wouldn't actually be able to see it with the naked eye. It would be very small. So the last thing I wanted to talk about is combinations of permeable and superconducting shielding. And there's more examples in my textbook, Applied Electromagnetics Using QuickField and MATLAB, published by Jones and Bartlett Learning. In this simulation, we have a transverse field or a sideways field, and we have a layered superconducting and mu metal disk here. Now, the mu metal is going to tend to channel flux lines through it, and that's going to screen some of the sideways field here. So this sort of illustrates a combination of shielding. So if you want to design a magnetic shield that attenuated both components of field that were along the shield axis and sideways fields, which superconductors are not very good at screening, then you might consider some combination of mu metal and superconducting shielding like this.